Welcome to the command center of today's explainer. We are stepping right into the shoes of a lead process engineer to tackle one of the most high-stakes, hyper-precise manufacturing pipelines on the entire planet. We're talking about engineering glass threads, optical fibers literally thinner than a human hair that carry trillions of data streams every single day. From your daily video calls to massive global bank transfers, the margins for error here are, well, essentially zero. All right, let's map out our production floor blueprint. We'll be looking at 1. Purifying the quartz foundation, 2. Vapor deposition and preforms, 3. Precision drawing under thermal stress, 4. High-speed shielding and cooling, and finally 5. Quality control and robotic assembly. Section 1. Purifying the quartz foundation. We're kicking off our chronological pipeline right at the molecular level. Because as any process engineer will tell you, your final product is only ever as good as your starting materials. Our absolute baseline requirement here is 99.9% pure silica quartz. To really put that into perspective for you, we can only accept one single impurity per million parts. We are talking about maximum allowed contaminants measuring in the millionths of an ounce per pound. To actually pull this off, manufacturers use vapor phase chemistry. They convert quartz into a gas, distill it, and then deposit it as a pure vapor inside sterile clean rooms that frankly look a lot more like aerospace labs than your typical glass workshop. So, why go to all this trouble? Well, it completely comes down to preventing something called attenuation. You see, even a billionth of an inch of foreign metal, or just a tiny bit of trapped water, will cause attenuation and crash our data transmission over long distances. Without this intense molecular purification, a light signal that's supposed to travel 60 miles would just get absorbed and disappear entirely. Section 2. Vapor deposition and preforms. Let's step into those sterile labs and see how we actually build the macro-scale foundation of our optical waveguide. We can't just draw a fiber from a random puddle of glass. We have to build a highly engineered template first, which we call a preform. We use the Modified Chemical Vapor Deposition, or MCVD process. By carefully injecting pure gases into a rotating, heated tube, we vapor deposit tiny droplets of silica soot, layer by microscopic layer. This lets us engineer the exact refractive index difference between the inner core, which carries the light, and the outer cladding, which traps the light inside. Finally, we hit it with extreme heat to collapse that tube into a solid, massive glass rod. That's our preform. Section 3. Precision drawing under thermal stress. Next up, we take that perfectly engineered solid glass preform and literally drop it into our drawing tower. This tower is a massive vertical structure, usually over 15 meters high, and it houses arguably the most thermally volatile zone in the entire factory. Just think about the extremes here. We feed this massive 25mm preform into a furnace blazing anywhere from 3400 to 4700 degrees Fahrenheit. The glass softens just enough, kind of to the consistency of warm caramel, and gravity takes over, pulling a continuous, incredibly delicate 125 micron flexible glass thread down from the tip. That single massive rod can be elongated into up to 40 kilometers of continuous fiber. It's wild. But here is an absolutely incredible engineering challenge. How in the world do we maintain a perfect 125 micron diameter when this molten thread is traveling faster than a cyclist moving through a city? We're talking speeds of over 1,000 feet per minute. The secret is real-time sensor data. We have this robotic feedback loop that acts with literal split-second precision. Non-contact laser micrometers are constantly monitoring the fiber's thickness. If there's even a fraction of a micron of drift, the automated control systems instantly adjust the drawing speed of the capstan wheel at the bottom of the tower, or they tweak the furnace temperature. This constant telemetry is absolutely crucial to prevent structural defects that would otherwise just ruin the fiber's optical properties. Section 4. High-speed shielding and cooling. At this exact moment in the drop tower, our new glass is flawlessly pure, but ridiculously fragile. If it's exposed to dust or even ambient moisture, microscopic defects form instantly. So we have to lock in its structural integrity immediately. This whole high-speed cooling and shielding phase happens before the fiber even touches a single physical pulley. In mere fractions of a second, the glass passes through a pressure die filled with liquid polymer. Right after that, it zips through intense ultraviolet lamps. The UV light instantly polymerizes and cures the resin into a solid protective shield, all without thermally damaging the underlying glass. We actually apply this in a highly deliberate dual-layer strategy. There's a soft primary coating that acts like a shock absorber to dampen mechanical vibrations so the fiber can bend. Then, a rigid secondary layer acts as armor against dust, moisture, and microscratches. This specific coating strategy allows the pristine silica glass underneath to retain its inherent 2 million psi tensile strength. Crazy as it sounds, if kept absolutely pristine, that glass is actually stronger than steel under tension. Section 5. Quality Control and Robotic Assembly. Let's head down to the diagnostic floor, where our engineering teams basically simulate decades of physical stress to mitigate future failure risks. Before a single strand gets packaged, it goes through a serious quality control gauntlet. Down here, we use advanced lasers and mechanical rigs to verify every single millimeter of that fiber. We use an OTDR, that's an optical time domain reflectometer, shooting light pulses to hunt down microscopic backscatter from hidden defects. We subject the fiber to tensile testing of up to 200 kilopounds per square inch of strain, and we run it through intense 4-axis bend tests. We are literally simulating the physical torture of real-world installation to make sure it never fails out in the field. I love how one of the engineers described this process. They said, "The spool moves smoothly to the left then to the right with millimeter precision. One wrong angle and everything will go haywire." That high-stakes precision is so vital during spooling. After QC, automated systems wind the fiber onto massive spools, adjusting rotation speed and tension with absolute surgical precision. They use lasers and cameras to ensure miles of fiber perfectly coil without creating a single microcrack. One slight misalignment, and a crack could ruin a cable meant to span an entire continent. Finally, we take these individual, incredibly fragile threads and armor them into rugged cables that can survive some seriously severe environmental hazards. Robotics bundle the fibers into flat ribbons or spirals, placing them inside flexible buffer tubes filled with a water-blocking, vibration-absorbing gel. This gives the glass some much-needed room to expand and contract as temperatures change. Then, we fortify the core with Kevlar or fiberglass and wrap the whole shebang in rugged PVC or polyethylene outer jackets. Depending on where these are going, process engineers customize that final protective layer against very specific deployment threats. For instance, deep ocean submarine cables actually need to be built thinner to handle extreme pressure and massive deployment lengths. But on the flip side, the cables laid in shallow coastal waters, those have to be heavily armored with corrugated steel just to survive devastating impacts from things like ship anchors and fishing nets. To wrap up this explainer, I want you to consider a pretty provocative final thought. 95% of the world's international data, from global financial markets to your late-night streaming binges, relies entirely on this invisible network. Despite all of our extreme, high-stakes engineering, the entire digital world still hangs by a beautiful, fragile, glowing thread. It really makes you wonder, as our data needs grow exponentially, how much further can we push the limits of a single strand of glass? Keep that in mind the next time you connect to the world.